Today we are going to calculate electric field due to a uniform ring. So there is a uniformly charged ring which has a total charge of capital Q. Okay, so this charge capital Q is distributed uniformly on this ring, and at a point P we need to find out what is the total electric field at this point due to this entire ring. Now in order to do it, we divide this ring into small parts, and let us say that we talk about this small part here which has a length of dx and a charge of dq. Now you know that in order to find electric field due to a charge, we just draw a line first, and the direction of that line gives you the direction of electric field. So suppose that due to this small charge, the total electric field is dE vector. Now let us say that this angle is theta, so this angle will also be theta. Now this electric field dE vector will have two components. One will be dE cosine theta and the other will be dE sine theta. Similarly, if there is another, let us say that we talk about another part of this ring which is exactly opposite to this dx, and it has also a length of dx and it has also a charge of dq. Then due to this charge, the electric field at this point will be in this direction, and because the charge is same dq and dq, so the electric field will also be same due to both these part of rings. And this angle, because they are at the same distance, this part and this part from this point, so this angle will also be theta and this angle will also be theta. Now if we just talk about only this part of the vector, so if this is vector, this angle is theta, so you can have, we're just talking about this vector. It makes an angle theta with the x-axis and the y-axis. So due to this vector, this vector along the x-axis will be dE cosine theta, and along the y-axis it will be dE sine theta. So it means that the vectors along the y-axis, because they are equal in magnitude and opposite in direction, so they will cancel each other. While these vectors, they are pointing in the same direction, so they will add to each other. In the similar manner, if we take any other 2 points, let us say this and this, two parts of the ring, they will again have x components in the x-axis and y components will be opposite to each other. So all the y components, they will cancel and will only have the x components. So it means that the total electric field will only be the x components, which is dEx cosine dE cosine theta. So in order to find the total x component of the electric field, we integrate this and we'll get Ex will be integration of dE cosine theta. Now because we're talking about a part of charge in this ring, so you know that the electric field is given by Ke dq upon r squared. So dE will be Ke dq upon r squared. So this integration will be Ke dq upon r square cosine of theta. Now this integration, it is an integration only on the charge. So we can take everything else outside the integral, and it will be ke cosine of theta upon r square integral over the total charge. Now you know that the total charge is plus q on this ring, so this integral, so this whole will be equal to ke cosine theta divided by r square into q. Now what is r here? R is the distance of charge from the point where we want to find out the electric field. So this distance was r in this figure. So if we have to find out r in terms of a and x and cosine theta in terms of a and x, what we'll have is r will be equal to x square plus a square under root, and cosine theta will be x upon r. So let us replace all of these quantities here. So it will be ke cosine theta will be x upon r. What is r? Under root of x square plus a square. And what is r? R squared. So it will be x square plus a square into q, the total charge. So this will become ke capital Q x divided by x square plus a square 3 upon 2. So this will be the total electric field, which is the electric field in the x-axis, and it is also the total electric field because we'll have electric field only in the x-axis, as all the y components, they will cancel because of the opposite parts of the ring. Now let us study a few cases based on this expression. So now let us say that case 1 is let us say we have to find out if the charge is at x is equal to 0. Okay, so if x is equal to 0, electric field will be 0. So it means that this means that if we have to find out the electric field at the center of the ring, it will be 0, because if x is equal to 0, electric field is equal to 0. Now in the case 2, suppose that if x is very greater than a, so it means that we're talking about a point which is extremely far away from the ring. So if x is very greater than a, then the electric field will be ke qx divided by, because x is very large, so let us take x common, so it will be we have taken x common and taken it outside the brackets, so then electric field will be keq upon x squared. Okay, so now this expression is similar to expression for a point charge, so it means that the ring will behave like a point charge. As a point charge when we're talking about a point which is very far away from the ring. Okay, now the third case will be Let me just write the expression for electric. The third case will be when x is very less than a. So when x is very less than a, we can take x outside, and what we are left with is this expression. So we say that it will be x square upon a square plus 1 if we take x square outside. Okay, so we've just taken this common, a square. So if we take a square common, it will be x square upon a square plus 1 and a square in the brackets. So because x is very less than a and a is very greater than a, so this quantity it will be equal to 0. So the electric field will be a square raised to the power 3 upon 2. So it will be KEQX divided by a cube. So this will be the electric field due to ring at a point which is very near to which is very near to the ring. Now all these cases we have studied for a positive charge. When we are talking about this point, it means that we have a very small positive charge here, the test charge. But instead of this, if suppose that the test charge is a negative charge, so if test charge is negative, then the electric force will be, because you know that electric force is electric field per unit charge, so in this case it is a negative charge, so it will be minus q. So the electric force will be KE capital Q, sorry, I think I have electric field is equal to electric force per unit charge, and the charge is negative, so we write minus q. So from here the electric force will be minus q into electric field, and electric field is given by KEQX upon a cube. So this will be minus KE small q capital Q upon a cube into x. So this will be the total force acting on a charge when it is brought near to the ring and it is negatively charged. So what is the meaning of this now? It means that when, now this is a sub case of this, x is very less than a. So that is why we're continuing with this expression. So when x is very less than a, it means that we are very near to the ring, and if the charge is very near to the ring, it means that it will experience this kind of force. Now this kind of force is, what is the meaning of this force? It means that this entire is a constant. A is constant, charges are constant. So it means that force is proportional to negative of x. Okay. Whenever we have a situation like this where force is proportional to negative x, it gives rise to a simple harmonic motion. Now it means that if you bring a charge near a ring and it is very near to the ring, then it will experience a simple harmonic motion near the center of the ring. Okay, that's all for now.